So last time we talked about parallel processing as a lead up to MapReduce, and we ended up with this schematic here in the context of this example where we're counting words across a set of documents, which is sort of the canonical example to start thinking about programming in MapReduce. And so each one of these vertical black lines represented a document, and we split them into smaller sets and sent each one of those sets to a separate machine. And then we applied our map function to each one of those documents in turn. And so if the map function, if you recall, took a single document and produced a set of pairs, and each pair was a word along with a count of the number of occurrences of that word in that document. Variations on this that you can imagine. Okay. Now, this word may have appeared in multiple documents, one here, one on this machine, one on this machine, and so on. And so now we need to group them all together onto a single machine so that we can count them. And that's exactly what this shuffle phase did. Okay. So here I've written 4 different tasks, processing, sort of looking like it's processing a single group at a time. But, I want you to think about how many map tasks are we going to have and how many reduce tasks are we going to have. Well, the map tasks are 1 per document. We have to call the map function. How many invocations of the map functions are going to be? Well, we're going to call it once per document. How many invocations of the reduce function are going to be? Well, it's the number of groups that are produced by the output of the map function. In this case, it's once per unique word appearing in any document. Okay. And so, in some sense, the number of machines we need to apply to this problem is maybe kind of predictable in the map phase. It's corresponds to the size of the input data set, which we presume to know. But the number of reducers we're going to need is maybe not known ahead of time, right? It depends on the size of the map output. Here we might be able to reason about it because we maybe know how many words there are in the English language, and we can assume that with a big enough set, all of those words will be represented at least once. But in general, it's dependent on the output of the map, so you don't really know. Okay, and so the only point I want to make is that we made a decision here to draw it as 4 different machines, but it may be the same 6 machines you use the map phase. It may be 1,000 machines, and so on. Nothing's stopping you from sending all of the word occurrences to a single machine and having this one machine process the green group, then process the red group, then process the blue group, and so on. Or maybe you would do 4 at a time because there's 4 cores in the machine. Okay. But that wouldn't be perhaps as efficient because it would be doing a lot of serial work. At the other extreme, you might think, well, we're going to need millions of tasks. Let's allocate, hundreds of thousands of machines to process them so that each machine is doing very little work. Okay. And that might make sense, but then the trade-off is perhaps sort of spinning up all these machines and preparing them to do the work. Okay. So there's a decision to make there, and we'll come back to that. Okay. But let's talk a little more about MapReduce itself. I'm belaboring this for a reason, because what I want you to do is start thinking in terms of MapReduce. Every problem you have, think, what if the data set was absolutely enormous, way too big for one machine? How are we going to split it into pieces? And a very good way of thinking about how to split things into pieces is to think about how you'd write a MapReduce program to do whatever it is you're trying to do. And so this is, yet again, the same example, just drawn in a different way. So here, the input is document ID followed by a value, and the value here is the entire text of the document. And the map function, just to make this clear, produces a set of things, not just one thing. Then they're shuffled to produce this. So this is word 1 with a count of 1, word 2 with a count of 1, word 3 with a count of 1, and so on. And then on the other side, what we get is word 1 with a group of all the occurrences, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then finally the reduce function counts them all up and finds that there's 25 occurrences. Okay. So I'm probably, I guess if this is completely obvious, you can always fast forward. I guess one of the beauties of doing this online. Okay. So fine. So what is MapReduce? Well, that's the programming model we just described, and there's a paper in 2004 that's on the reading list that describes this. And there's a couple of key motivations for doing this in that paper that I think sometimes get lost when you hear about the popularity of MapReduce today. And we'll talk about those two benefits in a moment. So one thing to realize is that MapReduce refers to the abstraction, and it's the name given to it by the authors of this 2004 paper. Hadoop is an implementation of MapReduce that came a few years later and was written by some people at Yahoo originally and then became an open source product that is managed by Apache and has lots of contributors. Okay, so the key idea for MapReduce was really this programming model, which it says here, right? Now it had a system with it as well, but the programming model being able to express lots of different tasks and have some sort of implementation automatically turn that into a parallel job turned out to be pretty powerful, right? This was an attractive way to write parallel programs, again, because you didn't actually have to worry about the parallel. All you did was write a serial map function and a serial reduce function, and the parallelism happened for free. And so the evidence that this is not so much about the system as it is the programming model is that you see MapReduce implementations appear in other contexts. There's people who have implemented MapReduce over GPUs. There's people that have implemented MapReduce on multi-core machines in shared memory. There's people who have implemented MapReduce on high-performance computing platforms, on groups of mobile phones, and so on. Okay. So this goes back to one of the motivations for this course, where I want to focus on abstractions where possible as opposed to tools. And so we're talking about MapReduce, the programming model, but we'll spend a little bit less time on the specific implementation, Hadoop, although you will have a chance in an optional assignment to work with Hadoop directly. Okay. So fine, so what is the data model of MapReduce? It's this bag of key-value pairs. What I mean by bag is a set that might have duplicates in it, right? And so we've seen that before. The document ID with the value, that's a key-value pair. Sometimes on the input, we'll be a little sloppy and not worry about precisely what the key and the value is. For example, if you're just given a record, you can assume that it's, say, the entire record is the key, okay? Or a document, sometimes even, we may not have a explicit document ID, but you can assume the URL or the file name or something is the key. The output of the mapper, though, the distinction between key and value gets really, really important because that's what controls the shuffle, as we've seen in that example. Okay. And so both the data model here is all about key-value pairs, and the input is going to be a set of key-value pairs, and the output is going to be a set of key-value pairs. And the point is that the set of key-value pairs can get arbitrarily large, right? We're going to be able to process this set no matter how big they get. There is kind of an implicit assumption that the key and the value are small. And small here doesn't necessarily mean very, very small. It just means that it needs to fit on one machine. There's no support for if value grows to be terabytes, it's not going to work. And so a document fits on one machine. That's okay. An image fits on one machine, and so on. Okay. So fine. So the map phase, as we've said, you provide a map function. The input is an input key and an input value, and the output is a bag of intermediate keys and values. It doesn't have to just produce, taking a single input to produce a single output. It can produce a set of things. And we saw this with the word count example. A single document came in, but a set of things came out. That's okay. All right. And then the reduce phase, what you're given is the intermediate key. This will be the same intermediate key that was produced by the map phase, right? One instance of the same intermediate key produced by the map phase, and then a bag of values that were associated with that intermediate key. And they may have, and the important thing here is that they may have come from any mapper whatsoever. The grouping into this bag of everything that shares the same intermediate key is handled automatically by the system. Okay. So the system will group all pairs with the same intermediate key and then pass that bag of values to the reduce function. And the implementation details of whether this is actually handed to you as a bag or whether it's an iterator, if you're familiar with that term, that you can step over, is implementation dependent, but it's not important to think about. It's a collection of values. Okay. Fine. So here it is all in one slide. The map function takes a in key and an in value and produces a list a bag of out key intermediate value pairs, and the reduce takes an out key and a list of intermediate values and produces a list of out values. I don't think I like this slide. I think I prefer the earlier one. The one thing I will mention is that the terms map and reduce, I tried to motivate that in the last segment, where you can think about converting a TIFF image to a PNG image. You can think about mapping, a function that maps every TIFF image into some PNG image. And that's where the term came from. And if you look back, this kind of came from the functional programming community. They use these terms. It doesn't precisely mean the same thing, but it's inspired by that. Okay. All right. So here's maybe the implementation for the example we have. And a lot of times what I like to do is sort of ask you to pause and think and stare at this code for a little bit and think about what it does. Here we've kind of gone through the example a lot, so I'll reveal the secret. But it's still instructive to work through this for a moment yourself. And in fact, maybe I'll end this segment there, and you can stare at this and make sure that you understand what it does.